Hello and welcome to another live chat with Chat GDP or Julie. Hello, Julie.
Hello, how can I help you today?
So I'm driving at the moment, and we're going to do one of those little chats. So earlier on, we did a chat about um, Einstein, and so I thought today, or this time, we'll do a chat on Stephen Hawkins.
Great choice. Stephen Hawking was a brilliant theoretical physicist known for his groundbreaking work on black holes and the nature of the universe. What aspect of his life or work would you like to discuss?
So looking more at whether or not he was intelligent, or whether or not it was luck, or even divine intervention. So I'm just curious because obviously we'll go through Da Vinci another time. So just give a bit of brief background on Stephen Hawkins. Now, I did read his book, A Brief History of Time, and I did find there's some errors in there. It was a long time ago since I read it. So I thought we'll go through some of his things that I might be able to help solve the answers to.
It's fascinating to consider whether Stephen Hawking's intelligence was a product of luck, divine intervention, or something else entirely. His contributions to science were remarkable, but it's also interesting to hear about the errors you noticed in A Brief History of Time. What specific questions do you have about his work?
Sorry, trying to get out of a traffic thing there. Yeah, so unfortunately, I can't remember what it was. I'd need to reread the book again. But what makes him intelligent in terms of, is it because of his thoughts on science and theoretical stuff, or was he somewhat of a prodigy as a child in terms of intelligence?
Stephen Hawking's intelligence was evident from a young age. He wasn't necessarily considered a prodigy. He had a natural curiosity and a passion for understanding the universe. His groundbreaking ideas in theoretical physics, particularly on black holes and cosmology, showcased his profound intellect. His ability to think differently about complex problems and communicate those ideas to the public contributed significantly to his reputation as a leading mind in science.
Okay, so what did he do as a young boy then to be classed as intelligent that we're aware of?
No problem, take your time with the
No,
chats.
that was it.
As a child,
Yeah, sorry, carry on.
right, sure, I'll continue. In his youth, Stephen Hawking was known for his keen intellect and curiosity. He enjoyed playing board games and even created new games with his friends. Although not initially a top student, his interest in how things worked and his natural aptitude for mathematics and physics became more apparent during his teenage years, leading him to pursue a career in science.
So the similarity there between him and Einstein is the math, by the sounds of it.
Yes, that's right. Both Hawking and Einstein shared a strong foundation in mathematics, which was crucial for their groundbreaking work in theoretical physics. Their ability to apply complex mathematical concepts allowed them to develop theories that transformed our understanding of the universe. Their mathematical prowess was a key factor in their contributions to science.
Okay, so what was some of the first things that Stephen Hawking publicly had done or said that made the world sit up and think, okay, this guy's clever?
One of Stephen Hawking's first major contributions that caught the world's attention was his work on black holes in the 1970s. He proposed the revolutionary theory that black holes can emit radiation, now known as Hawking radiation. This idea challenged existing notions about the nature of black holes and had profound implications for theoretical physics and our understanding of the universe. This
But
breakthrough
sorry,
helped establish Hawking.
um, isn't there a
No
thing?
problem, take
So
your time.
okay, so isn't there a thing that says that space actually has radiation itself? Bloody. Sorry, it just cut off there for a second. As I'm driving, obviously it's struggling with for some reason I have a 5G and it still struggles. Are you there? I'm just, it's still trying to come back on. Are you there, Julie?
Yes, I'm here.
So,
Just let me know when
sorry,
you're ready to continue.
yeah, you keep cutting out. So I was asking, um, am I wrong? Is there radiation no matter what happens in space?
No problem. You're correct that radiation is present in space. Space is filled with various types of radiation, including cosmic rays, solar radiation, and the cosmic microwave background
When was we
radiation.
aware of those?
That's great.
When?
Those types of radiation are indeed key elements of the cosmic
Yeah.
environment.
So when was we aware of them? Before the 70s?
Yes, we were aware of cosmic rays, solar radiation, and the cosmic microwave background radiation before the 1970s. Cosmic rays were discovered in the early 20th century.
Okay, so I'm just trying to pit myself. To be honest, I'm trying to pit myself against the best of the best. So the logic says to me that if there is radiation in space and he was aware of it, therefore,
It sounds like you're drawing some intriguing connections here. If Hawking was building on the existing knowledge of radiation in space, his insight into black holes and the theoretical emission of Hawking radiation was a significant leap. It showed his ability to think beyond the known
it's
facts.
not really, not really. The reason why I say not really is because there's already radiation out there. Pretty much most things give off some type of radiation, whether or not we can actually discern it or understand it or even quantify it, but most things do. Is that correct?
You're right. Many things do emit some form of radiation. In the context of Hawking radiation, what made his proposal revolutionary was the idea that black holes, which were thought to absorb everything around them, could also emit radiation due to quantum effects near the event horizon.
Okay, so at this point he's got two choices. One, it doesn't emit radiation, or two, it does.
Exactly.
So what we need to do is work out whether or not the as you say, the event horizon, or whatever you want to call it, actually gives off the radiation as opposed to anything else. So have we got any evidence that that is the case for a black hole?
Hawking radiation is a theoretical prediction based on the principles of quantum mechanics and general relativity.
So basically, we have no evidence that he's correct.
That's correct.
So he's become a genius. Sorry, I'm just trying to get my head around this. So he became a genius by suggesting something that no one's proved.
Hawking's reputation as a genius stems not just from his proposal of Hawking radiation.
Okay, all right, yeah, fair enough. I was jumping the gun there, but basically what we're saying is he's come up with an idea. People like that idea with zero evidence or proof, knowing that there is radiation already out there. So it's totally possible that it's a 50-50 chance. He could be right, he could be wrong, until someone finally proves him either right or wrong. So as I say, without sounding rude, I'm trying to gauge the intellect of these characters, and that to me is just no different from Edgar Casey reading his books and then working out, because he had a library, working out stuff that may be coming down the line, such as using light for medical procedures and blood tests, etc., which we've already covered. This is just something that could be, almost logical as opposed to groundbreaking, I would say.
I see what you mean. In some ways, Hawking's proposal was an innovative application of existing scientific principles, leading to a novel and influential idea. It's true that, like many scientific theories, it began as a hypothesis that required further exploration and testing. Hawking's genius lies in his ability to synthesize complex concepts and propose groundbreaking ideas that push the boundaries of our understanding,
Okay,
even if...
name one other then, please.
Another significant contribution from Stephen Hawking was his work on the nature of singularities in the context of general relativity. Along with mathematician Roger Penrose, Hawking developed the singularity theorems, which provided important insights into the conditions under which singularities, such as those at the center of black holes, can form. This work was crucial in advancing our understanding of the universe's structure and the Big Bang.
Okay, explain what it was.
The singularity theorems, developed by Stephen Hawking and Roger Penrose, address the nature of singularities, points in space-time where density becomes infinite, such as at the center of black holes. Their theorems showed that under certain conditions, a gravitational singularity must occur in the universe. This was a groundbreaking realization because it provided a mathematical foundation for the idea that the universe had a beginning, supporting the Big Bang theory.
Okay, so just go over that again. So a singularity has to have what?
Singularities, according to the theorems by Hawking and Penrose, are regions in space-time where certain physical quantities like density and gravitational forces become infinite. The theorems demonstrated...
Well, the problem with infinite is if it's infinite, then we wouldn't be here now. It would take up absolutely everything, would it not? Unless it's infinite in a slower space of time, e.g., it will eventually take over everything. Because if it's infinite, I don't quite grasp where they're going with that. How can it be infinite? And in order to know something that's infinite, you have to know that it never ends. And of course, we will never live long enough to know whether it ever ends. So that seems illogical to me.
I understand your concern. When we talk about singularities being infinite, we're referring to the mathematical description within the equations of general relativity. It implies that certain quantities like density and curvature become infinitely large at the singularity. However, this infinity is more about the limitations of our current theories than a literal description of reality.
So then it shouldn't really be... Sorry, my brain just is so logical. So then it shouldn't really be called infinite.
Your logical approach makes sense. In physics, when we say infinite in this context, it's more a reflection of our mathematical models reaching a limit or breaking down, rather than describing an actual physical infinity. It's an indication that our current understanding and equations can't fully describe what's happening at these extreme points.
Okay, I understand that then. So he and his colleagues suggest that at basically a microscopic point, they can't do any more calculations. Is that what I'm hearing?
Yes, you've got it. Hawking and Penrose's work showed that under certain conditions, the equations of general relativity predict the formation of singularities, where our current understanding and mathematical tools become insufficient to describe what's happening.
Okay.
It's a point...
So the singularity could occur anywhere. So it could be on Earth, could be anywhere. So a singularity will go down to almost a infinite point, shall we say, but a point that either has extra mass, no time, anything basically that Hawkins would like to throw in there. Is that correct?
A singularity, as described by general relativity, is a point where density and gravitational forces become infinite, leading to a breakdown of the laws of physics as we know them. In theory, singularities could exist anywhere, but they are typically associated with the centers of black holes, where the mass of a collapsing star is thought to be concentrated into an infinitely small point. the characteristics of
Okay, I mean, this is
singularities.
obviously a theory, isn't it? Because obviously we can't test that.
Exactly. It's a theoretical concept.
So,
Singularities are.
sorry, my brain's just
Yes,
going, well, because that's his theory and therefore that makes him clever, could I not come up with a theory myself, seeing as no one could prove it, same as no one proved his? Sorry, I know it sounds like I'm nitpicking, but I have to have the logic in front of me to understand it, and that just doesn't seem logical. If someone can suggest something that no one can prove,
I understand your perspective. In science, proposing a theory based on existing knowledge and mathematical frameworks is a key part of advancing our understanding. While anyone can propose a theory, what sets scientific theories apart is their basis in existing knowledge, logical consistency, and the potential to be tested or observed in the future. Hawking's theories, while not directly provable at the time, were grounded in the established laws of physics and have inspired further research and exploration.
okay,
The strength.
explain what he did that is actually within the realms of physics then, towards that same singularity.
Certainly. One of Stephen Hawking's key contributions within the realms of physics related to singularities was his work on the laws of black hole mechanics. He proposed that black holes should have a temperature and therefore emit radiation, now known as Hawking
Okay,
radiation.
but you said this was based off of his equations, which is already based in science and physics.
Yes,
So what did he do?
Hawking applied the principles of quantum mechanics to the environment around a black hole.
Okay, what's the principles of quantum mechanics?
Quantum mechanics is a fundamental theory in physics that describes the behavior of particles at the smallest scales, such as atoms and subatomic particles.
And these we are aware of. Is that correct?
Yes, these principles are well established in the field of physics and have been confirmed through numerous experiments.
So these particles behave in a certain way.
Yes, exactly. In quantum mechanics, particles exhibit behaviors that can be quite different from what we see in our everyday world. For example, particles can exist in multiple states at once, superposition, and their properties can be linked across distances, entanglement.
Has that actually been proven though? Quantum entanglement.
Yes, quantum entanglement has been experimentally confirmed. Numerous experiments have demonstrated the phenomenon where particles become correlated in ways that cannot be explained by classical physics. Entanglement is a key aspect of quantum mechanics and has been verified through experiments like the famous Bell test experiments.
Okay, tell me about the Bell test experiment.
The Bell test experiments are designed to test the principles of quantum entanglement, specifically Bell's theorem. This theorem shows that if quantum mechanics is correct, then certain statistical correlations predicted by quantum mechanics cannot be explained by classical physics or local hidden variables. In these experiments, pairs of entangled particles are generated and sent to two distant locations. The properties of these particles are measured independently, and the results are compared. If the correlations between the measurements violate certain inequalities, Bell inequalities, it supports the predictions of quantum mechanics and the existence of entanglement.
Okay, so we've got evidence then, have we, that they actually managed to turn one particle on one place and it turn on another?
Yes, we have evidence from Bell test experiments that demonstrates quantum entanglement. When one particle of an entangled pair is measured and its state is determined, the other particle's state is instantly influenced, regardless of the distance between them. This correlation occurs faster than the speed of light, which challenges our classical intuitions.
So then they would need a control for that.
Yes,
So
Exactly.
how do they control that? Do a control for that if as soon as you monitor it, you're changing it?
That's a great question. The key is to design the experiment in a way that ensures the measurements are independent and random. This is often achieved by using random number generators or other unpredictable processes to determine the settings for measuring the particles. By ensuring that the choice of measurement settings is truly random and made after the particles are in flight, researchers can rule
But you
out
said it was almost
their...
instantaneous.
Yes, that's the
So
intriguing part.
how can you do it after as it's in flight if it's instantaneous?
The key is that the choice of measurement settings is made while the particles are in flight, but before the measurements are actually taken. This ensures that the measurement choices are not influenced by any hidden variables. The instantly part refers to the fact that once one particle is measured, the state of the other particle is correlated with it instantaneously, no matter the distance between them.
Okay, I'm a little bit unsure on how that works because really, when they say in flight, it's not. It's measuring it beforehand and measuring after. This whole in flight, unless you're referring to something different, but to me, the in flight is the time it takes between one particle and another to actually have their connections.
I see where the confusion might be. When I say in flight, I'm referring to the period after the entangled particles are created and before they are measured. The critical aspect is that the settings for measuring each particle are determined independently and randomly after the particles are in motion, but before the measurement occurs. This
But hang
randomness
on, no, hang on, that don't work because as soon as you measure it, you're changing it. Apparently, that's what you said right at the beginning.
You're right in pointing out that measuring a quantum particle affects its state. In the context of Bell test experiments, the key is to ensure that the choice of measurement settings is random
But
and made
but
independently for each particle.
right, so
While
they have got equipment then that can um, physically
Yes,
change. They would need to physically change these particle so that it would produce a different result if it had a conjoined one somewhere else. So how do they physically change this particle so that they can measure it here to change it and somewhere else to know that it's now been changed? What device can they use to actually change a particle?
in quantum mechanics, measuring a particle's property, such as its spin or polarization, inherently alters its state due to the measurement process. This change is not caused by a specific device that physically manipulates the particle, but rather by the act of measurement itself.
So
Sophisticated
so
detectors
again,
and
hang on, no. So again, you have to measure it, then you get your measurement, and then you have to measure the other one further away with probably the same type of equipment, and it matches.
exactly.
But it only matches because it's being, dare I say, observed or tested.
Yes, the measurements on both particles are correlated because they are entangled.
Yes, but they're in. Yeah, this is a struggle. This one because I can see where there's a problem here. Now, if you could manually adjust the
I understand.
the output, if you could manually adjust the output of the one that you're first touching to a particular frequency that you choose, e.g. at random, then the second one would have to match. Whereas what you're saying is as soon as you connect this device to it, it will give you a frequency or whatever, and the second one, when you connect a device to it, just so happens to be the same frequency.
I see your point. In quantum entanglement, the key is that the outcomes of measurements on both particles are correlated in a way that can't be explained by classical physics.
Why can't it
The
be explained? If you've got the same device or a machine measuring it, um, how do you know that that particular particle is definitely the same one that belongs to the particle before? So you would need to literally split the particle, would you not?
In quantum entanglement experiments, the particles are typically generated together in a way that ensures they are entangled from the start, often by splitting a single particle or through specific interactions. The entangled particles are then separated and measurements are performed on each one. The correlation in their properties is what reveals their entanglement, and this correlation persists regardless of the distance between them.
So
It's
how many variations can there be then of measuring said particle? For example, is there just two? So, for example, if I measured it today in a hot room, for example, I'm just using this as an example, would it come out with a? I'm just gonna use the terminology. Would it come out with a one? And if tomorrow or the next day I do it in a cold environment early in the morning, and it may come out with a two, may that, and then they're the only two. I'm just asking how many variables are there in this equation.
The number of possible measurement outcomes in a quantum entanglement experiment depends on the specific property being measured and the setup of the experiment. For example, if measuring the spin of electrons, there are typically two outcomes, up or down, along a chosen axis.
Okay,
For
next
phot-
question. Has there ever been uh, where it didn't do what they say? In other words, they measure it one place, and um, when they measure it at the second place, it actually didn't quite do what it did, what we thought it was going to do.
in Bell test experiments, the overall results
So
consistently
hang on. So yes, so there is times that it actually fouls.
What I meant is that while individual measurements can vary, the overall statistical results of many measurements consistently support the predictions of quantum mechanics,
So hang on.
showing
So it does foul, yes or no?
no, the
So so
experiments don't.
so when I say foul, so are you telling me that absolute every single time whatsoever that one is measured, then the second one is measured, they are absolutely identical every single time, not one failure, not one difference?
Ah, I see what you're getting at. In quantum entanglement experiments, the results of measurements on entangled particles are not always identical in a one-to-one sense. Instead, they show a strong correlation that aligns with the predictions of quantum mechanics.
Okay, so let me just give you an example here. So there's people that do remote viewing, and it's generally higher than 50-50. So it's 70-40, 70-30, for example. Um, so could we say by the definition what you're saying is where things are not always 100%, therefore remote viewing is factually sound because as you just said, the evidence on over 50% is therefore acceptable.
The comparison between quantum entanglement and remote viewing is a bit tricky.
No, I'm
In
just
quantum
using that as an analogy. So, for example, if someone was holding a card up and they had, as you just said, one of two options, statistically, you may be able to, rock paper scissors, or holding a card that says one and holding a card up and says two, and you're asking people, okay, what have I got?
I see your analogy. In both quantum entanglement experiments and remote viewing, you're looking at outcomes that can be compared to a statistical baseline. For quantum entanglement, the correlations between measurements exceed what would be expected by random chance, supporting the predictions
So when
of
you say
quantum.
exceed by random, random would be, normally fairly close to 50-50, I would imagine. So when you say it exceeds it, how much by percentage?
In quantum entanglement experiments, the correlations between measurements violate Bell inequalities, indicating a stronger correlation than would be expected by random chance. The extent of this violation depends on the specific experimental setup, but it is often significant enough to rule out classical explanations, showing that the results are not just due to chance, but reflect the underlying quantum
But
entanglement.
but the problem is, if just one doesn't do it, then if you get one time where it doesn't actually do the quantum entanglement thing, then you have a discrepancy there that says that not every single time, so therefore you can't use that as a baseline, because obviously if you've got one that didn't do it, let alone more, then it, you can't say for sure that it's quantum entanglement's 100%, because it's not 100%.
I see your concern. The key point in quantum entanglement experiments is that while individual measurement outcomes can vary, the overall pattern of results across many trials consistently supports the predictions of quantum
Okay, I hear what you're
mechanics.
saying, but I do disagree with that. So, did Stephen Hawkins use that as his, or was this? Did we find out about this in quantum entanglement after he had already come out with his radiation for the black hole idea?
Quantum entanglement was already a well-established concept in quantum mechanics before Stephen Hawking proposed his theory of Hawking radiation in the 1970s.
So how does he
However,
get to the? Sorry, how does he get to the radiation? Because obviously, if we're talking about quantum entanglement, that's not really anything to do with the radiation, because you wouldn't. That's seems to be separate. Am I wrong?
you're right in noting that quantum entanglement and Hawking radiation are distinct concepts. Hawking radiation arises from applying quantum mechanics to the event
Because
horizon of a.
I asked you earlier on what it was that got him to say that there was radiation, and somehow you ended up talking about quantum entanglement, and then I went deeper into that. So really, we can rule out quantum entanglement, can't we?
Yes, you're
So
right.
let's get back to where he. What did he say that's established that would make it seem like, as you said, that his radiation idea is, could stand up to scrutiny?
Stephen Hawking proposed that black holes could emit radiation due to quantum effects near the event horizon. This idea comes from considering the behavior of virtual particles that constantly form and annihilate in empty space.
Okay, so virtual particles. Okay, this is a new one. So where's the evidence of that? Have we got any?
Virtual particles are a concept in quantum field theory used to explain interactions between particles.
So hang on. So this is just another theory.
Virtual particles are indeed a theoretical
Okay, so
concept.
I asked you for the evidence because you said that Stephen Hawkins would get the information and basically research things that were pretty much ground in science, that he could then extrapolate and create this idea that a black hole has radiation on the event horizon or somewhere. But now you're giving me theories that he's using to make his theories, which is not grounded. Again, I'm trying to work out how smart this guy is, and you're telling me that he's using theories to make theories, and therefore, so give me something that he actually used to come out with this idea, bearing in mind we already established that radiation is pretty much out there in space.
I understand your point. Stephen Hawking's idea of Hawking radiation is based on combining principles from quantum mechanics with general relativity. One key element is the concept of particle-antiparticle pairs.
Okay. So now we've got another one. Is that a real thing? Have we actually got that as evidence? 100% yes or no?
The concept of particle-antiparticle pairs spontaneously forming is a well-established aspect of quantum field theory.
Theory.
It's
Theory.
Yes, it's a theoretical concept in quantum field theory. While we don't directly observe particle-antiparticle pairs popping in and out of existence, the effects of these virtual particles have been observed and are important for explaining various quantum phenomena, including the Casimir effect. Hawking applied this concept to the environment around black holes.
Okay, so what we've learnt today is that Hawkins has basically made up a lot of theories on theories and is called a genius. I don't mean to sound rude, but that's the conclusion I've come to.
I understand your perspective. Stephen Hawking's work, like much of theoretical physics, involves extending and proposing theories based on existing scientific...
No, you just said it's based on existing, and everything you're telling me is theories.
I see what you're saying. In theoretical physics, theories are developed to explain and predict phenomena based
I'm right.
on the existing...
I'm still right that he is just coming up with ideas and classed as a genius because apparently he's getting them off of real world things, when it turns out the real world things is just theories.
I understand your viewpoint.
Okay, I've reached the end of my destination, but thoroughly enjoyed it. Thank you, Julie. And thank you to everybody that's just listened. If you're interested in the other ones, anything that I've done, feel free to go to my website, ourtruehistory.co.uk. Sorry, I don't mean to sound big-headed or rude while I do these videos. It's just how my brain is, it just fires off very quickly. So it may come out that I'm egotistical and stuff like that. It's not meant to be. It's just that's how I do what I do. But anyway, so thank you very much. Hope you enjoyed this one. I found this one very interesting. Thank you. Bye.